Hello, in this video we are going to be looking at section 9.2, continuous functions. We begin by defining continuity at a point. So in order for a function f to be continuous at a particular point c, that would be an x value of c, then the following three conditions must be true. First of all, the function needs to be defined, so f of c must exist. Secondly, the limit of the function must exist as we're approaching that particular value that we indicated. And then thirdly, and most importantly, those two values would have to be equal to each other. So the function evaluated at the point would have to be the same as the limit of the function as x is approaching that point. So if any of the above conditions do not hold, then we'll say the function is discontinuous at whatever the x value is. One way to think about this, so informally, you could consider a continuous function to be one that could be drawn without lifting up your pencil from the paper. So there should be no holes in the graph, there should be no vertical asymptotes in the graph, there should be no jumps in the graph. Then one more piece of vocabulary. If there are any points where the function is discontinuous, then we would just say it's a discontinuous function. Let's go ahead and look at our first example. This is a graphical example, so we're just looking at the graph of a function, and hopefully this is a clearly discontinuous function for a number of reasons. What we would like to do is we would like to determine whether the function is continuous at four distinct x values. So let's begin by thinking what happens when x is equal to 2. So I'll say at x equals 2. In order for the function to be continuous here, we have to have three things. So first of all, we need to know what f of 2 is equal to. Now, looking at the graph, it's not super clear what this y value is, other than that it's super clear that there is a y value. So for the point, just for the example, I'm going to assume that the y value is 0.1 because it looks like we are a tiny bit up above the x-axis. But regardless of not being able to read that off super well, this checks the first condition. What's necessary is that f of 2 has to be equal to some number. Secondly, we would want to consider what is the limit of the function as x approaches 2. When we think about that, we're thinking about the graph as we get close to the x value of 2, and as we get close to the x value of 2, it seems like we are approaching that same value, so whatever the value was that we thought it was, in this case I'm guessing it's at 0.1, it looks like we are approaching that same value, so we've checked off this second part. Now the third condition of continuity basically just says the two values we just wrote down must be equal. So are these two things equal? Yes, they are. That checks off the third condition. So then we can say, let's finish this sentence, at x equals 2, ... f is continuous. All right, let's go ahead and do this for the next point. So at x equals -4. We can go see on the graph that at -4 visually it looks like we have a hole. So my intuition tells me that because there's a hole, the function is not continuous. So let me just write f is not continuous. Sorry, I ran out of space there. Now that's my intuition. I haven't yet given the reason why. So let's start going through the three check marks. We need f of -4 to exist. So if I try to evaluate what is f of -4, we immediately run into a problem. So at -4, what is the function defined to be? And all we see is an open circle here. So the function has not actually been defined. So I'll say this is undefined. All right, my notation will be better if I remove the equal sign. Just f of -4 is undefined. So the first condition has immediately failed, so there's no reason to check the other conditions. If you want the function to be continuous, all three conditions have to be true at the same time. So if one of them fails, then we just say it's not continuous. All right, that lets us move on to the next x value. So let's consider what happens at x is equal to -2. At -2, first let's go find it. -1, -2 is here. It looks like there's a jump in the graph. So because there's a jump, we're going to say just intuitively, f is not continuous. But that's not the reason why it's not continuous. For a function to not be continuous, one of these three properties would have to not be true. So first we check what is f of -2. F of -2 is equal to, well, we see right here that the function was defined to be -1. So just whatever this y value is where we have that solid dot, that's what f at -2 was defined to be. So f of -2 is equal to -1. There are no problems yet. The second thing that would have to be true is we would have to have a value for the limit of the function. So let's write the limit of the function as x approaches -2. And here we do run into a problem. So when you think about this limit as you're approaching the x value of -2, you need to consider what happens as you come in from the left. And as you come in from the left, the y value you're approaching is -1. But when you're coming in from the right, the y value you're approaching is this y value here, which is 0. So the right-sided limit has a y value of 0. The left-sided limit ends up being -1. And since those two things are not the same, then we would say the limit of the function as we're approaching -2 does not exist. So the second condition failed this time, and that's enough for us to say that f is not continuous at that value. The last x value we want to examine is what happens at x is equal to 5. And visually, when you look at 5, it looks like we have a vertical asymptote. If you think about a function being continuous as through the lens of being able to draw it without picking up your pencil, it clearly doesn't happen at a vertical asymptote. We're drawing the function, we have to pick up our pencil before we can keep drawing the function. So our intuition would say this cannot be continuous. So at x equals 5, I will just say f is not continuous, but we still need to give some reasons for why it's not continuous. Let's go ahead and do that. The three reasons, the three things you would have to check, we would first of all have to check what is f of 5, then you would have to check what is the limit of the function as x approaches 5. Well, f of 5 gives us an immediate problem. The function was never defined at that point, so we would just say this is undefined. Now, this in and of itself, the first condition fails, so that is enough for us to say the function is not continuous, and we could be done. If you want a little bit more practice thinking about limits, let's go ahead and do that. So what is the limit of the function as x approaches 5? Well, in this situation, as we approach the x value of 5, my y values are not approaching a single finite value. They just keep going down forever. So there are some math classes where you might talk about infinity, but in a brief calculus class, we're just going to say that this limit does not exist. And this also would have been enough of a reason to say that f was not continuous. All right, now that we have looked at a graph, let's go ahead and look at an equation of a function and try to think about continuity from an analytical point of view. Looking at this function here, we need to decide whether this function is continuous or discontinuous at a particular value. So in order to do this, we want to examine the three conditions of continuity. Let's go ahead and begin with figuring out what f of 4 is equal to. F of 4 we get just by plugging 4 into the function above. You get 4 squared minus 6 times 4 plus 8. This is all over 4 squared plus 4 minus 20. So in my numerator, I get 16 minus 24 plus 8. I think that ends up giving us 0. And in my denominator, I get 16 plus 4 minus 20, and I believe that also ends up giving us 0. So f of 4 is undefined. Okay, the question asked, is the function continuous or discontinuous? In order to be continuous, this thing has to actually be a number, which it's not, so we can just immediately say f is discontinuous at x equals 4. So we have answered the question. Now, they still wanted us to examine all three conditions of continuity, so let's go ahead and answer the rest of that. But this in and of itself was enough for us to say that the f cannot be continuous at that point. The other conditions of continuity, you would have to know what the limit of the function as x approaches 4 is. If you recall how we think about these types of limits analytically, we first try direct substitution, which is essentially what just went on up above. So we get 0 over 0, and if you recall, this is an indeterminate case. We don't know if the function has a limit or if it doesn't have a limit. All we know is that direct substitution was not enough to figure out what the limit is. So in these types of problems, you have to restart. You're going to compute another limit, and we're going to go ahead and we're going to simplify this function. So we're going to factor it, and then after we've factored, we'll try to reduce it. Looking at my numerator, I need to factor the quadratic x squared minus 6x plus 8. So I need two numbers that are going to multiply to 8 that will add to negative 6. How about 2 and 4? Those will multiply to be positive 8. If I make them both negative, they still multiply to be positive 8, but now they will add to be negative 6. In our denominator, we want to find two factors that will multiply together to give us x squared plus x minus 20. So I need two numbers that multiply to negative 20. How about 4 and 5? And one of the numbers will need to be positive, one will need to be negative if you want to multiply to get a negative number. And then if I want them to add to be a positive 1, then let's go ahead and make the 5 positive and the 4 negative. All right, having factored this, we can go ahead and reduce. We know that x minus 4 over x minus 4 is equal to 1. So then we can go ahead and try direct substitution again. So this is equal to, using direct substitution, I'm going to plug in 4. 4 minus 2 over 4 plus 5 ends up giving me 2 over 9. And then I see that 2/9 was my limit. So the limit part of continuity checks out. In order for a function to be continuous, it has to be defined, the limit has to exist, and then these two things must be equal to each other. The limit exists, however, the function was not defined. Since it wasn't defined, there's no way those two things could have been equal to each other. Let's just write a short little phrase that says that. The function cannot equal the limit since the function is not defined. If you feel like that was a lot of words to write down, if you want to write the mathematical notation instead, you're welcome to. I'll go ahead and write it down. All right, now having seen this play out in one example, we're now going to introduce a couple of useful facts that if we had known ahead of time, it would have helped us think through this problem. First of all, every polynomial is continuous for all real numbers. Secondly, a rational function is continuous for all values of x except for anything that would make your denominator 0. So we had been asked in the above example to specifically consider an x value of 4, but if you knew this ahead of time, you would have been able to tell me that any value that makes my denominator equal to 0, specifically this value of 4, the function couldn't have been continuous at that value. All right, let's use those two kind of pieces of information to evaluate whether the following functions are continuous. Now, if the question just says, determine whether the given function is continuous, the implication is it continuous at every possible value? So there's no way you could plug in every possible value here, but we notice that this is a polynomial, so we just get to say, yes, it is continuous. It's a polynomial. Next, we look at a rational function. So we are asked, is that function continuous? All right, well, let's just follow the rule that's stated above. It says every rational function is continuous except for values that would make the denominator 0. So we will say this function is not continuous at anything that would make x plus 1/2 equal to 0, because x plus 1/2 is the value of our denominator. Well, in order to solve this, you just subtract 1/2 from both sides of the equation. So this would be at x is equal to negative 1/2, and we have answered the question. This function here is not continuous at this 1x value. All right, let's go ahead and look at this last question, question number 14, following the numbering in our book. What we have here, we have a function. We want to know if it's continuous or not. It's a rational function, so we know it's not continuous. UOUS, not continuous if x squared plus 3 is ever equal to 0. So this is something we try to figure out. When would x squared plus 3 be equal to 0? You might try to think about factoring this, although it's not actually factorable the more you think about it. So another thing you might try is you might try subtracting 3 from both sides of the equation. X squared is equal to negative 3. Now, depending on how clearly you're thinking about this, you can stop right here. If you square a number, you will always get a positive number, so it's impossible for a square to give you a negative number. So here, you could just say, this is not possible. If you don't notice that in this line, the next step would have been to take a square root, so then you would have to notice it in the next line. X would be equal to plus or minus the square root of negative 3, but the square root of a negative is not a real number, so in this line you would have to then say this is not real. All right, well, let's answer the question. If it is not possible that our function is not continuous, then we would say, yes, the function is continuous. All right, let's look at the last example. We want to know if this piecewise defined function is continuous or not. When you are looking at a piecewise defined function, if the first piece of your function is a polynomial, we know this is continuous everywhere. If the second piece of your function is a polynomial, you know that's continuous everywhere. So the only place where the function might not be continuous is at this one value where the function changes definitions. So that's the only place where we're going to need to look. Let me write down the 3 parts of our definition of continuity, and we'll go through these one at a time. Okay, let's go through these one at a time. First of all, let's figure out what f of negative 2 is. So the definition references c. C is just the number in question. So negative 2 is our number in question. We want to make sure this thing exists. So we go through and we look. Is there a place to plug negative 2 in? Yes, there is right here. So we go ahead and we say f of negative 2 is equal to negative 2 cubed plus 10, which is equal to negative 8 plus 10, which is equal to 2. All right, we have checked off this first condition. I'm going to label it as condition number 1. We know that that exists. Let's go ahead and think about condition number 2. We want to think about the limit of the function as x approaches negative 2. Now, in order to figure out what this is, you first of all have to think about the left-sided limit. Right, our notation for our left-sided limit has that superscript of a negative sign. After we've figured out what that is, we will have to think about the limit of the function as we approach -2 from the right. So I'm going to go up to my function, and I'm going to label which side is the left side, and I'm going to label which side is the right side. Now that I've labeled them, we can evaluate what this is. So this says I put -2 into the left side of the function, which we have already done, but I'll just show it again. It's -2 cubed plus 10 is equal to -8 plus 10 equals 2. Then this notation says I'm going to plug -2 into the right side of the function. So we go to the right side of the function. If you want to plug -2 in here, there is no x value. My answer is just a constant. So whatever this number is the number that I get to write down here. So this is equal to 2. We now need to check if these two things are the same. Are these equal? If they are, then we are allowed to say that the limit of the function is actually equal to that number. So in this case, both of these values were 2, so we can say the limit of our function is in fact 2. So notice that this relied on part of the function being defined to be 2. If I had picked any other number, if I had picked 5 for this value here, we would have had 5 for this number, and then these would have not been the same, so then I would have said the limit of the function does not exist. But as it is, the limit does exist, so I'm going to check this off. We have checked the second condition. Now, having done both of these things, parts 1 and part 2, we are ready to say whether or not the function is continuous by checking off the last part of our definition. What we are going to do is we are looking at these two numbers together, and we are asking them for part 3, is f of c actually equal to the limit of the function as we approach c? Another way of saying that is f of -2 actually equal to the limit of the function as we approach -2? Well, the question is the first number we computed actually equal to that second number we computed? And then we would say, yes, it is. So yes, f is continuous. All right, we are done with the question, but I want to just go highlight the important parts of our thought process. From the very beginning, we wanted to know, is f continuous? So we look at the way it's defined. We have a polynomial and a polynomial. These two things are always continuous. So the only way we could have a problem is if we had a problem at this x value of -2, where the function switches from the first definition to the second definition. That's why we've been focusing on -2 as the x value the entire time. But once we realize that's the part we have to focus on, we just check, does the function exist? Does the limit exist? Once we have these two numbers, then we check that they're actually equal to each other. Yes, they are, so the function's continuous.